It's really my great pleasure to welcome Naoki Yoshida as our speaker today, at least virtually. He has worked on many aspects of cosmology and has pioneered research in the first stars, how I know him, but obviously in most of computational astrophysics, as you know, he was discussing with Stefan just right now. He received his PhD from the Max Planck Institute for Astrophysics and the University of Munich. And after a short stint as postdoctoral fellow at Harvard and as Japan Society for the Promotion of Science fellow, he joined the faculty at Nagoya University first and then moved to the University of Tokyo, where he's professor at the Department of Physics. And today he will talk about cosmic relic neutrinos and large-scale structure, nonlinear clustering and neutrino mass. Thanks. Naoki.
Okay, thank you, Marta, for introducing me, and thank you for the organizers for inviting me. I'm very happy to give this talk remotely, although obviously I really miss visiting Paris in physically, but sometime soon I really do want to visit there to meet many of you face to face. Let me share my screen. Okay. Okay, do you see the full screen? Okay, is this looking okay?
Everything's perfect.
Thank you. All right, the bottom picture is a snapshot of Fugaku computer. This is the Japan supercomputer. Currently, the fastest, world #1 on this planet. And today I am going to use this biggest computer to detect neutrinos. What do I mean? Instead of using Cherenkov telescope or instead of using photomultipliers, I use this biggest computer. And then I'm going to tell you how, okay? Now, the main topic today is the cosmic neutrino background, okay? To avoid some confusion with C and B, hereafter I call C nu B, okay? C neutrino background. This is the generic prediction from the standard Big Bang model when the universe was very hot and dense. There was and there is an ample of relic cosmic neutrinos that permeate the universe. And since 1 second after the Big Bang or so. Okay, so the right panel shows the typical cosmic evolution, and we are familiar with the C and B, but technically or in time-wise, C nu B came from much earlier epoch, basically. The present day temperature is just about the C and B temperature. The number density is similar also. And in fact, in the early universe, then the energy contribution was also high, like this. About 10% of the cosmic energy density was dominated by or contributed by relic neutrinos. This is interesting, but it's just currently in the present day universe, it permeates the universe. It's very hard to detect. So in fact, the neutrinos are the minimalist. They don't have a charge, they have 0 size, and possibly 0 mass. So what else they want, I don't know. They are very simplest particles. But only the last point, it's possibly 0 mass, but we know that the neutrinos might have a finite mass, okay? Because actually the neutrino oscillations have been discovered for atmospheric neutrinos and the solar neutrinos, which led to the 2015 Nobel Prize in Physics. And for many reasons in particle physics and cosmology, the absolute mass scale is extremely important, but is largely unknown. All we know is the mass difference among the species of flavors of the neutrinos. So we know there are 3 generations of neutrinos, 3 flavors or 3 mass eigenstates. but the mass hierarchy as depicted on the right, we don't even know how it is, let's say, organized, or how the mass is distributed among the three. So one normal hierarchy case is this, possibly with the measured mass difference, or possibly inverted hierarchy like this. Sorry about that. It's energy density contribution just scaled with the total mass of neutrinos in this way. So long time ago, neutrinos were thought to be the dominant contribution to dark matter. But by now we know, already in early 1980s, we know that neutrino cosmology doesn't really work, because if neutrinos are dark matter, the structure should look like this. With these large thermal motions, they can hump or they can clump only in large galaxy clusters. And this overall distribution of neutrinos as dark matter is completely different from what we observe as galaxy distribution. So this is the real galaxy distribution. So for these reasons, neutrinos are not really the dominant contribution to dark matter. However, more recently, we noticed the importance of the existence and the effect of neutrinos on the large scale structure. But as elementary particles, it's very hard to detect. Okay, so here I want to illustrate how hard to detect the neutrinos. So here's a solar system picture. Suppose you can fill this solar system up to, say, Pluto, the orbit, with this heavy element, lead, Pb. I don't know how much amount, but suppose you can do this to fill in completely the solar system. Actually, for neutrinos, solar neutrinos, nothing happens, basically. Most of the solar neutrinos just escape, even though in this sphere ball of lead. All we can possibly do is, if we fill with the lead, these heavy elements, to 50 times beyond the orbit of Pluto, then about half of the neutrinos from the sun can be detected or can be captured. So, in other words, still 50% of the solar neutrinos can escape out of this huge amount of lead to 50 times the Pluto's orbit. So such an elusive particle, basically. About its mass, it's promising, but the available constraints are limited. Interestingly, our cosmological constraint is doing better. So here I list the state-of-the-art constraints on the neutrino mass from particle experiment, the scattering experiments. It suggests the electron neutrino mass should be less than 1 electron volt. Whereas by now we have CMB and other large-scale structure proof that suggests the total mass of a neutrino. At EAP, you are familiar with this Planck result. It must be less than 0.1 electron volt or so. Well, on both sides, the future sensitivity is great. With upgraded scattering in a few years, it gives the sensitivity of 0.2. And the proposed project 8 phase 4 experiments, it's going to be 0.04, whereas for cosmology, CMB plus large scale structure and so on can come down to 0.03 electron volt. So we can also discern the normal or inverted mass hierarchy or so. Just a quick review of the experiments. So scattering experiment is gigantic, let's say it's like dome or the apparatus or detector. This detects the emitted electrons from tritium decays, and it measures the emitted electron energies. So this is an impressive picture when people were distributing this scattering tank in the city of Karlsruhe. The most interesting thing is actually these most of these German people, they seem to be like ignorant of this event, interestingly. Anyhow, this is a gigantic experiment. the result is like this. This is the as a function of electron energy and count rate. And all we are concerned is this the endpoint of the energy distribution, the so-called Curry plot. Depending on the neutrino mass, this endpoint behaves differently, and the energy distribution looks slightly different way. But this sensitive measurement can discern this difference between the massless case and one electron volt mass case, and so on. Okay, so this is the current best ground-based experiments. Now, cosmological proof. In cosmology, we do very different things. We do not detect directly the neutrinos themselves, but we measure the dynamical effect of the relic neutrinos on structure formation. So we have this large-scale structure, galaxy distribution, and we can calculate the distribution power spectrum in this way. Interestingly, this matter power spectrum is affected by the existence of relic neutrinos and by its mass, total mass. So this black line is for the massless case, whereas this red line, 1 electron volt, this looks like this. And you know the precision cosmology. We can discern this power spectrum difference, at least statistically. Okay. There are many issues like galaxy bias and so on, but in principle, one can detect, or one can discern this difference to measure the neutrino mass from large-scale structure. The point is, you can just imagine the hot particles or thermal relics are distributed in the universe, and then one can define the critical wave number or critical wavelengths owing to the free streaming of fast neutrinos. The typical velocity dispersion is like this. It also scales inversely to the neutrino mass. And then this power spectrum dumping is called. So effectively by measuring this power spectrum dumping effect, one can get either the velocity dispersion or the effective wave number, critical wave number, which tells us about the neutrino mass, okay? So in this way, one can use a large scale structure as a proof of neutrino mass, okay? The point is, we need accurate modeling in the nonlinear clustering of matter or galaxies. One can do the same thing from CMB lensing. Again, I'm sure people at the IAPER, you are familiar with this. One can have this CMB fluctuation, CMB lensing measurement, reconstruction of density field. Then we can get this, lensing power spectrum. Then similarly for massless case, all the way up to say total mass 0.3 electron volt. And statistically, one can discern or detect this difference. Okay. So cosmology, the future is bright, but again, we need accurate modeling. Good. This is a snapshot from one of our recent simulations, and including both cold dark matter and massive neutrinos. Also today or in this talk, I call this C nu B background. We do see a significant clustering for neutrinos, especially when they have a finite mass. Okay, so in this case, the neutrino mass is 0.2 electron volt or so. Then you can see this correspondence between the CDM density fluctuation and corresponding neutrino density fluctuations. Although the amplitude is much smaller, so it is only like in log 0.2 or so, compared to the CDM density enhancement in galaxy clusters like this. But all of these, say, collective effect will affect the statistics like the power spectrum and so on. Okay? And from our simulations, I tell you more in detail, but one can also measure the effective neutrino temperature, the local velocity dispersion in this way. And we see like neutrinos can be hotter or colder depending on where we are in the universe. But again, this relative amplitude is only the 10% level effect. Okay, how we got these results? This is the basics. So to follow the structure formation in the universe, basically with dark matter and neutrinos, we need to advance the collisionless Boltzmann equation. So in its appearance, it's very simple, like this, basically advection equations, coupled with Poisson's equation for gravity. Okay, so gravitational force centers here. So in principle, for a given initial condition, cosmological initial conditions, the evolution of the velocity distribution function in 6-dimensional phase space should be just followed, coupled with Poisson's equation for gravity. You can easily imagine this is very high. This is really the curse of dimension, because we need to follow the evolution in 6D, 3 for space, x, y, z, and 3 for momentum and velocity. Only memory-wise, to store the distribution function on 64 power 6 grids, it needs 270 gigabytes. If we want to run more realistic, like 512 to the power 6 grids, it needs 70,000 terabytes of memory. Okay, 7 times that are available on Summit, a US computer. So this is really a nightmare. So mostly this large memory consumption hampered us to do the direct simulation. But I want to remind you, or I will show you that currently, as of this year, simulations with this size can be actually performed on the Fugaku computer. And then we can do, say, reasonably good job to follow the phase space structure for relic neutrinos. This is the, again, the snapshot of the computer. It has 158 nodes, and each node has 52 cores. And these numbers, well, numbers are numbers. Simply, this is the biggest one and the fastest since last year. In many aspects, like in the speed and utility for AI, machine learning, and energy consumption, and so on. So this is a nice one. Okay. We ran cosmological simulations for the best fit cosmological parameters, and then we vary the neutrino mass because in the end, we want to discern the subtle effect caused by the neutrinos. Okay. We also vary simulation volume from 200 megaparsec to 10 gigaparsec or so. And this is the largest simulation we could perform on the currently available computer. So this is a craziest number. Even for the CDM particles, we spent about 7,000 to the power cube. So we want to show the sort of fresh, brand new result. However, okay, so this is the nice snapshot. Only recently, last month, we could perform the full scale run. So this is 1 gigaparsec volume and usual dark matter distribution. And we also see, this nonlinear clustering of relic neutrinos. So they are not just neutrino background, but they do cluster, they do cause the local effect and so on. Okay, so more later. However, before presenting a brand new result, I would like to pose a question. So, suppose we want to do cosmological simulation and we want to have a big one. What's wrong with just distributing many particles? Okay, because we are so familiar with N-body simulations, cosmological N-body simulations. Why don't we distribute like trillions of particles representing neutrinos and so on? This is a very basic question. So here I have an interesting experiment. We have a good N-body solver. So we can easily run 2 million particle simulations on my laptop. Okay. We also have direct Boltzmann solver in full phase space, but maybe poor resolution, 64 to the power 6 or so. Okay. Here I simulate a very simple equal mass galaxy merger. Okay, so perhaps the movie would be one of the most boring movie you have seen this year, but let me show anyhow. This is a simple merger. Each body represented by 1 million particles merged and go through and 2 humps again. Okay, it's like watching a very old movie. The same one by direct Boltzmann equation solver. Similarly, very boring. We have seen this many times before. Galaxy merger, stellar cluster merger, and so on. Now, if we look at, I can move this around, I wonder. Okay. If I look at the velocity structure, this is very different. So instead of showing X, Y, Z positions of particles, here I show the velocity structure at a given point, so Vx and Vy for this merger remnant. If we plot by our Boltzmann solver, we see 2 humps because this is like was an equal mass merger. So each body had a diagonal velocity vector. If we do the same thing with 2 million particle simulations, we just see this particle distribution. Again, this is the velocity distribution, not the spatial positions. Even if we smooth it, we don't see, we can barely see these 2 slight humps. And in low density regions, we still have this full velocity structure, but with particle simulations, we don't have any such. So this is a sort of state art. Very interesting. And I figured out, we simply calculate the velocity power spectrum for this. We get this nice smooth velocity power with a strong damping down to very low level. But if we calculate the velocity power spectrum with the particle simulation, we see this short noise like this. So essentially, from this comparison, I can conclude to see this smooth velocity power spectrum, velocity structure, we need about 10 to the power 11 particles per object. This is outrageous. Curious, at least in the momentum space or velocity space, we have been dealing with this poor resolution. But so far, at least, we were not really aware of any bad aspect of this. Turning to the neutrino distribution, I already showed this left panels, density distribution, and temperature distributions. Let us try to do the same thing with particle simulations, like using 1500 cube particles. The density distribution look okay, with some particle shot noise. But the velocity distribution, this is bizarre. We can't really see any correct velocity moment. Okay, so this is again curious, but again, density structure looks sort of okay. There are some like slight dilution or coarse sampling in this physical space, but the correct temperature or correct velocity structure can be followed only if we really solve the 6-dimensional distribution function evolution. Okay, this is why we develop sort of custom-made or let's say special purpose Boltzmann solver for this topic. Okay, so these are only technical things. So we put a number of say improvements, ideas, and so on, especially to use the state-of-the-art supercomputers. And we also think about say time integration scheme and so on, all optimized for this neutrino program. Okay. Just to show a series of test results, you might wonder how this browser for Boltzmann solver works effectively. So in the next few slides, I show a simple result for the test cases. For example, this collisionless damping, very famous one. Here I show the distribution function in X, one-dimensional, and Vx. So, and we put on the perturbation on this. The overall evolution looks like this. And you see this phase space structure develops in a diagonal way. And there must be a critical wavelengths like Jeans wavelengths describing collisionless damping, and gravitational unstable case, and so on. Our simulation or calculation reproduce the linear prediction and also this nonlinear evolution part, especially we see this nonlinear oscillation quite accurately. Let me skip this very technical part. I just want to show that we do quite coding or programming by employing the state-of-the-art technique. Nonlinear random damping, if we work on plasma physics, this is extremely important, but we figured out, we do need a very high order reconstruction accuracy to preserve this very fine phase space structure. Again, this is X and Vx. So this is avoiding the artificial phase space mixing. Instead, if we employ the third order, lowest order ones, then we show this quite a smearing. Okay. Now, these are simple test cases. The other more extensive test cases are given in our previous papers, but now here I want to focus on our cosmological runs. So we have a hybrid solver, browser for Boltzmann for hot neutrinos, and usual n-body solver for cold dark matter. Okay, and they share the common gravitational potential. And the rest is pretty straightforward in this, in a sense. So we simply follow the evolution. Also, it's like memory consuming and so on. Okay, again, the same cosmology. This is the result. No impressive. We are familiar with this dark matter distribution, 200 megaparsec volume, corresponding neutrino distribution, like this. Okay, we see neutrino clustering. Okay. So these black contours are dark matter distribution. So we see in near superclusters, neutrinos are distributed with higher density. Bulk velocity field, one can also calculate this relative velocity between dark matter and neutrinos in this way. Neutrino bulk velocity field, like this. So they move around, they are like thermal relics, but they do have bulk motions induced by the large scale structure of cold dark matter. Also, this is a nice representation. This color scheme is the velocity structure, velocity distribution function. So you can simply imagine the three-dimensional Fermi-Dirac distribution with some certain temperature, plus bulk velocity. The effect of bulk velocity is seen as deformation of the low energy part, say below the energy scale of 300 kilometers per second. If we try to reproduce this velocity distribution with particle simulations, this is poor sampling. So there's no way of having the effect of high energy tail or high energy neutrinos in this way. Okay, we do need, for accurate simulations, we do need the full information of this velocity or momentum distribution of relic neutrinos. Okay, so this is why we could reproduce this as compared to the coarse sampling in particle simulations. I'm going to skip. This is a simple illustration how Fermi-Dirac distribution can be represented by finite number of particles. Okay. We also calculate the relative velocity. This relative velocity becomes later important because it causes the dynamical friction against dark matter component. So relative velocity distribution. Again, near the large scale structure, we see, say, the clear streaming of dark matter against the sea of neutrinos. Okay, the most important perhaps is the damping of matter power spectrum. So hereafter I show the dark matter power spectrum in runs with neutrinos, and we compare, we normalize the power spectrum of the case without neutrinos. Okay, so here the showing damping is really all relative sense compared to the neutrino-less case. How much power spectrum damping is expected. Okay. So this is the total neutrino mass 0.2 electron volt case. We see characteristic spoon feature like this. This is the linear damping, nonlinear transition, and this is a nonlinear clustering of dark matter. Okay, we use 3 different box sizes to get the nonlinear feature. Almost present day epoch, redshift 0 or so, we see this damping effect. In terms of neutrino mass, depending on the total neutrino mass, these 4 cases, we see clear difference in damping. But please remember this difference is, say, 20% or 30% effect, depending on the neutrino mass. Okay, so this is still hard to detect, but it's possible with future, say, galaxy redshift surveys and so on. Okay? So again, the light neutrinos, relatively heavy neutrinos. Also, I want to draw your attention with our comparison with the sort of analytic model of Mead et al. It's a kind of extension of Peacock-Smith's matter power spectrum calculations. The solid lines are full Boltzmann simulation. Although it was approximated, the analytic model by Mead et al. Does very well, actually. Even it predicts this, the bottom of the damping very accurately, depending on this neutrino mass. Okay, this is the redshift 0 and redshift 1 case. And dashed line, just to compare, dashed line is a linear or first order perturbation theory. So the nonlinear regime, we can't really use this perturbation theory to get accurate results. Also, there must be an effect on the mass function, as has been known. Again, the level is, say, tens of % level, but if we could, in principle, if we could measure the galaxy cluster abundance with this accuracy, one can discern the neutrino mass, redshift 0, redshift 2, and so on. So probably, technically it would be very hard, weak lensing, X-ray cluster, and so on. But there should be this difference depending on the exact neutrino mass. Okay, a little bit more involved statistics. This is like a neutrino density against the halo number density. So we want to have some tracer of neutrino clumping like this, and it turns out the halo over density delta H is a good indicator for the local neutrino over density like this. There's relatively a good tight correlation depending on this the exact neutrino mass. Okay, so maybe in the future one can use this relation to infer the local neutrino density field. Okay. This is even more, one would even say this is academic, but this is interesting. Actually, the local velocity dispersion or for neutrinos, hot or cold spots, it depends on the neutrino mass. Interestingly, if neutrinos are heavy, like relatively heavy, like total mass 0.3 electron volt, they are hotter in galaxy clusters. Whereas if the neutrinos are lighter, most likely in a universe like this, they are actually colder in galaxy clusters. This is in good contrast with the gas. Neutrinos are colder in galaxy clusters because galaxy clusters, this deep potential well can capture only the low energy component of massive neutrinos. So this causes this interesting difference. And to a different degree, the same thing happens for Milky Way halo. So Milky Way halo preferentially captures only the low energy relic neutrinos, basically. Okay. Finally, this will be the decisive signature of relic neutrinos. So suppose there is a permeating sea of neutrinos, and then a dark matter halo galaxy is moving against it. Essentially, the dark matter halo fills the neutrino window or so. As a back reaction, one can imagine this is there will be a neutrino wake or a smaller hump of neutrinos because of the relative motion of dark matter halo. And this will be ubiquitous because this is a dynamical effect. So this will be ubiquitous. For every galaxy halo, galaxy cluster halo, behind it, there must be a neutrino wake. Okay, so this causes a peculiar distribution pattern for neutrinos. Okay. Numerically, or from our simulations, we can actually detect or measure this neutrino hump caused by the dynamical friction. So here is a complicated plot. Here we align a galaxy halo, galaxy cluster halo, always so that their velocity vector points to the downward like this. And then we stack the neutrino distribution, and then we see this clear hump. This is caused by the back reaction of the dynamical friction against dark matter halo galaxies. Okay. And so this is, of course, angle dependent. This is like a line of sight and perpendicular direction. We plot this neutrino density, say like 10% difference can be seen. Again, this effect itself depends on the exact neutrino mass. In this case, 0.4 electron volt. There's a difference between 0.4 electron volt and 0.2 electron volt in this case. Obviously, it's easier to detect probably for massive cases, but even for relatively light cases, there exists a neutrino hump. So in a dream case, if we know all the galaxies' velocity direction, velocity vectors, if we can align all these galaxies and take the correlation function and so on, we should see this effect. There is a bit, say, promising or tractable, feasible way of doing this. If we have two galaxy populations or two galaxy, say, two density tracers, say, let me put like red galaxy and blue galaxies, or heavy galaxies and light galaxies. So they have different bias with respect to dark matter and with respect to neutrinos. So because of this bias difference, we have a cross term between these two populations. And especially they have different angle dependence with respect to the neutrino distribution in this way. So they must have say characteristic dipole term appearing by this cross correlation. So simply, suppose we take the cross correlation between heavy galaxy and light galaxy, and so there must be a coupling term. And this can be the signature of this anisotropic neutrino distribution. So we say, theoretically, we calculate this dipole term as a function of angle and as a function of radius or distance. Then again, depending on the exact neutrino mass, we see the difference in the amplitude of this dipole term. So in the future, if we can detect this dipole effect, then one can infer this neutrino mass, hopefully. Okay, let's not get desperate or let's not get disappointed. As you know, we will have very accurate, say, tracer, like a wide field galaxy distribution from Beryllium observatories, about half of the sky. And we have the CMB lensing measurement from CMB S4. We have Subaru PFS, three-dimensional galaxy distribution. We have Nancy Roman telescope for lensing and galaxy distribution and so on. So the simple estimate by Cora Dvorak and her colleagues, the constraint on the neutrino mass would come down to, say, tens of milli electron volts. So roughly, say, 0.0 something electron volt. So this is very promising. So the future large-scale structure probe would be very sensitive to the absolute mass of neutrinos through its dynamical effect on the large-scale structure. Also, particle physicists, experimental particle physicists do well. This is the proposed Project 8 cyclotron radiation emission spectroscopy, a super sensitive detector for the particle experiments. Okay, we also have in Japan hyperkamiokande direct neutrino detectors, and also many planned neutrinos double beta decay. So it also tells us about Majorana Dirac particles, or how the mass hierarchy is organized, and so on. For example, hyperkamiokande, it's approved already last year. Construction began. Its primary science goals is to discern the neutrino mass hierarchy or lepton sector CP violation, proton decay, possibly ground unification theory. So this is a gigantic water detector. One nice catchy example is if Betelgeuse explodes nearby, it generates a lot of neutrinos, supernova neutrinos. Then hyperkamiokande will detect a total of 60,000 neutrino counts. Okay, then depending on the exact neutrino mass hierarchy, normal hierarchy, inverted hierarchy, this is a function of time, arrival time of these neutrinos, and this event rates will be different depending on the exact neutrino mass. Only if it happens, say, in the next 20 years. All right, so both cosmology, particle experiments, they do very well. And theory-wise, for cosmological probe, we need to work more. Especially one caveat, I didn't talk about it. We haven't tested our code for the full nonlinear object. And here I'm showing a very nice example of your local colleague, Stefan Colombi. For example, dark matter distribution, because of the nature of cold component, it should have a very complicated phase space structure. And eventually we want to try to reproduce this phase space structure with our browser for Boltzmann solver. And then to see more insight on the structure of dark matter halos, for example, instead of thermal neutrinos. We can also adapt our code to test the variant dark matter models, warm dark matter, or Bose-Einstein condensate, action dark matter, and some recent hot topics. This is one example of shredding a Poisson simulation for fuzzy dark matter. We see typical wave interference patterns, and so on. One can also get full phase space distribution if we employ 6-dimensional Boltzmann solver. So we need to work on to get a better, more accurate result for neutrinos and for other dark matter simulations. To summarize, okay, the dynamical effect of the relic neutrinos is established. One can get accurate statistics by simulations. Observational precision cosmology, we need more signature. And then, particle experiments are doing well, but most likely for this critical mass range, the cosmological probe will be the most sensible, most powerful weapon for us to determine the neutrino mass. And currently we are planning to run simulations with 2 neutrino species to see the difference between a normal hierarchy and inverted hierarchy case. Okay, the effect should be subtle, but should be discernible with future galaxy surveys, I hope. Okay, variant models, variant theoretical models I already talked about. And finally, there should be many other applications, especially if you work on plasma physics. We share the same equation, same configuration, and so on. So there should be many more to explore. So I'm just about the right time, and I stop here. And then thank you for listening to my talk. Thank you very much.
Thank you very much, Naoki. It was wonderful. So questions?
I have something on my chat. Oh, okay.
Great.
Shall I answer to these questions actually? No.
Sorry, I'm confused. I don't see. Well, I see that Christophe has his hand up.
Okay, sorry. Maybe there was one question from Christophe by a direct message to me.
Okay, so that's why I didn't see it. Sorry.
Okay. No, okay. So Christian Pichon, he asked why I am comparing the say 2 million particle simulations with 64 to the power 6. Oh, okay. So he The question is about this comparison. Marta, are you still seeing this?
Yes.
Okay, good. Okay, so this.
I mean,
actually, good.
It's not in presentation mode, but we can see it very well.
Okay, but okay, let me do this. Is this? The question is, is this a fair comparison? Of course not. Of course, what I wanted to say is, 2 million particles, we believe it's enough. It's more than enough to resolve this, let's say, simple object. But in principle, if we want to have this nice velocity structure or accurate velocity structure, we need 10 to the power 11th particles per object, which is even undreamable also. It's outrageous. So we actually found with tuning and so on, our Brazov solver is even more effective than going for brute force particle simulation to achieve this number. That's the main message from this comparison. Okay.
Can I ask another quick question?
Yes.
Sure.
Yes.
What figure would you show us if you wanted to convince us that it's actually necessary to have a full Vlasov code rather than, say, Jeans moment-based code to address the problems of neutrinos? Do you know what I mean by Jeans moment-based? So you take the hierarchy of Jeans equation and you truncate it at some high order, but you don't actually follow the full phase space.
Oh, very good question. I want to say, okay, here I focus on the comparison with particle simulations. It also has some velocity moment, but the left side is like, say, I would say full Boltzmann hierarchy or full information on the distribution function. If we only take first order, second order moments of velocity, I don't know how well. Maybe you can see this hot part. Maybe you don't see this cold part and so on. But I or somebody else need to try and validate or verify those approximations. And simply, currently, I believe this full phase space information is the most accurate one. But it also depends on the resolution and so on. Okay. But it's a very good direction.
Gary?
Hey, hi Naoki. I enjoyed very much your talk. It was very clear.
Thank you.
I had a question of the following, which is that one method that people use to estimate cosmological parameters is the evolution of the halo mass function.
Yes.
So I work in Euclid with 100 people who are trying to do that, and so one issue is how well are our theoretical notions of the evolution of the halo mass function, And what you've shown is that, and of course, it's really at the high end that is very interesting. Yes. And what you've shown is that at the somewhat high end, fairly high mass neutrinos, I think you're taking 0.2 or 0.3 eV, we're making a factor 5 difference in at 10 to the 4 solar masses.
Yeah.
Your picture. Let me see now. At redshift 0.5.
0.5 redshift 2. So this is maybe your sweet spot.
So you see, if I look at redshift 0.5, I presume that your last grid is on the right is the left plot, but the rightest grid on the left plot is 10 to the 14 solar masses. This is 10 to the 14. This is 10 to the 15 here. Okay.
Yeah.
Okay. So, but still, so we'll be dealing with clusters of 10 to the 14.4 or something like that. And so I see effects going down to factors of 2, which are huge, which are even higher than the effects that we expect from baryons, okay, which are much more messy to measure.
Yeah.
And
Gary, you are right. You are very right. But if we have a direct mapping of some, I don't know, cluster mass estimate, weak lensing, member galaxies, even X-ray luminosity to this real mass function. This is, theory mass function. If we have a way to map accurately, and if we can discriminate between these two cases, then that's it. That's the thing.
Yes, absolutely. It means that the idea will be to solve for the neutrino mass together with the other dark energy parameters.
Exactly. But you are right. This is, in a sense, this is considerable. Thinking about many baryonic effects. This factor of 2 difference.
But the Planck limit being 0.1 is your cyan curve, and your cyan curve is showing only 10% effects.
Yeah. You're right. So this is going to be tough, but statistically, perhaps one can put an effort. So,
anyways,
like many other
very eye-opening.
Yeah. Yes.
So when do you expect to have I don't know if you'll merge forces with Stéphane Colombi, who's done remarkable work on his side, but when do you expect to see the cold dark matter handled with the Vlasov-Poisson model?
Okay. Yeah, we need to just increase the spatial resolution. Let me pull up. Essentially,
that's the problem with cold dark matter. You need a lot of resolution compared to the neutrino.
Yeah. So essentially, if we could run the browser solver, I need to resolve this galaxy clusters at least. So either we go for small volume simulation or do some zoom in technique, something like this. Then we will see the phase space structure. But that's I'm kind of planning.
Colombi worries about the fact that you have in 1+1 dimensional phase space, you have entangling. You have a spiral that develops, which gets more and more entangled, and then somehow, if I understood him correctly, he kind of smooths it once in a while. So do you have this issue too, and do you handle it in the same way?
To some extent, yes. And then let's see. I showed a nice test case of the 1D case. This is say X and Vx, so 1D case. We can nicely preserve this structure. But when this becomes a multi-dimensional, I can imagine some smearing or smoothing effect. So I really need to see what really happens in the very nonlinear 3D object. So that I should explore. Maybe in the future, in the near future, like adaptive mesh refinement or more some technical things. I mean,
interesting. Okay, thank you very much.
I would like to ask a question. So it just follows on what Gary just asked you. So I think, so you showed us how the standard particle simulations fail at some point, and you asked the philosophical question, so should we trust simulations with particles? And then you showed us a simulation where you actually use particles, for dark matter. So, I understand the technological challenge, but can you say, or what would be the possible problems that arise, I mean, in this particular problem from using particles for dark matter?
Martha, very good question. I really don't know, and I'm just curious about what you think you wonder about. And then so far we couldn't find any catastrophic error in the particle simulations. Our spectral mass function, they do more or less good. Only one exception is probably let me share again. This Neutrino wake, this is gonna be very hard to reproduce for particle simulations, obviously. But I haven't seen something like this before. But Martha, let me go even more. I have this secret slide which you put up. So one final question. Okay, I have been over 10 years. I have been always wondering why this is okay with 1 million particles. We never had a problem. I have 3 theories. Martha, you can read it later. You know, maybe we are not very sensitive to kinematic phenomena like velocity moments or velocity distributions. I speculate many things. Or velocity components aren't just important in dynamics, in some many physics. I argue strongly against, because I think in university you teach Hamiltonian mechanics, and position and velocity, they are conjugate. So either one should be like equal. Or our understanding of mechanics, physics sort of has been limited, or maybe has been only partial. We really need to fully understand nonlinear clustering, visualization, the origin of NFW profile, and so on. I don't know, Martha. Thank you for asking. This is my question.
I see your points, and I agree on most of them, especially the third. So thank you for sharing this with me.
Yeah, maybe your colleague with Stefan or anybody. I really want to continue exploring these things. Very good.
So any more questions? Gary, you still have your hand up. Do you have another question, or just leftover from before?
It's leftover. I'll take it down. Sorry about that.
Any more questions? Okay. So if not, I think we can thank Naoki again. And it's weird.
Thank you. Thank you very much. I enjoyed it too. Thank you. Thank you, everybody.